Well, an aerosol, the physical definition of it, it's a small particle which is suspended in the air, can be suspended at any altitude, but our main interest is in tropospheric aerosols, which are suspended at altitudes essentially from the ground to about 8 kilometers in the atmosphere. The total number of aerosols in the atmosphere is extremely large. It's like the number of stars in a galaxy. And those are tiny particles. Most of them are invisible to a naked eye, but there are very many of them. Aerosol particles can be natural and can be created as a result of human activities. And so those particles are called man-made or anthropogenic. Natural aerosols can come from all places. For example, desert dust is blown off the surface of the Sahara Desert, the Asian deserts, the Australian deserts. Sea salt particles are produced when ocean waves break. They produce a lot of tiny salt particles. Essentially, all kinds of fires produce aerosols. Volcanoes, they throw out a lot of volcanic ash, and those are also natural aerosols. And all kinds of human activities produce different kinds of aerosols, and the most typical example would be sulfate particles, the result of combustion, or soot particles. On average, an aerosol particle is estimated to live for about a week. Aerosols are produced, they're transported, and eventually they disappear because they are rained out, for example. Aerosol particles can differ by their size and by their chemical composition and by their shape. And all these inequalities can be mixed together, and that's what makes aerosols so difficult to study. At any given location, particles of different types and of different origins can coexist. If a particle is, for example, generated somewhere in China, it can be transported to the United States of America. So this transport from different places makes the aerosol population at any given location extremely complex. They have several roles in affecting climate. For one, they simply reflect sunlight back to space, and this effect amounts to cooling of the atmosphere and the surface. But the same particles can also absorb light, and by absorbing light they become warmer and they warm the surrounding air, so this effect is to warm the atmosphere. And how much light is reflected and how much is absorbed depends on the chemical composition of the particles, on their size, even on their shape. There's another effect that aerosols exert on climate because they affect the properties of clouds. And clouds are a major modulator of the amount of energy that reaches the surface and warms it. And so by changing the properties of clouds and precipitation, the aerosols can also affect climate. The most important knowledge that we have is that aerosol particles are extremely complex. So we need to study the distribution of particles globally, and the only way to do that is from satellites. The knowledge about aerosols that we have tells us that the instrumentation on this satellite must also be very complicated, and with this instrumentation we must be able to infer many properties of the aerosol particles from space. And that's the purpose of the aerosol polarimetry sensor, which will fly as part of the GLORY mission. We are not interested so much in their total number as how they are distributed, because their distribution affects local climate, and that's why we need to know this distribution with very high accuracy.